Hi, everyone. Good afternoon, and welcome to the webinar. This is the webinar series on the Water-Thermoelectric Energy Nexus, brought to you by the Center for Partnerships and Innovation at NARUC, as well as the Sandia National Laboratories. We would also like to thank the U.S. Department of Energy for their ongoing support of these initiatives. My name is Carrie Worthington, and I'm a Senior Manager at NARUC, the National Association for Regulatory Utility Commissioners. I'm here today joined by Commissioner John Rosales from Illinois as the moderator, and he will introduce the rest of the panelists. The format for today will be a 60-minute webinar. Sandia National Labs and the Renewable Energy Laboratory will be providing a 20 to 30-minute overview of their study on the characterization of power plant water use, and then we'll have about a 10-minute dialogue with Director of Palo Verde Water Resources at Arizona Public Service, Bob Lotz, and then we'll open the call to questions and comments from the audience. The format for submitting comments is through the chat functions and features of the webinar, so please use those boxes to be able to send in your chats, and we will feed those questions to the moderator. So thank you all for that. Without further ado, John, the floor is yours.
Thank you, Carrie, and thank you for allowing me to moderate this first webinar in a series of Water-Thermoelectric Energy Nexus webinars. This webinar series is inspired by President Jack Perkowski's vision of the energy-water nexus powered together. We commonly hear the expression water is the largest user of energy, and energy production uses the most water. We won't be myth-busting today, but that illustrates how interdependent these resources are. With concerns about the supply and demand of both water and energy in the future, Sandia National Labs set out to research integrating water into long-term transmission planning at the interconnection level. We will be hearing from two national lab folks on a study they are wrapping up on characterizing power plant water use. Vince Tidwell of Sandia National Labs and Jordan Machnick of the National Renewable Energy Laboratories. Vince is a principal member of the technical staff at Sandia National Laboratories. He has 18 years experience conducting and managing research on basic and applied projects in water resource management, nuclear, and hazardous waste storage and remediation, and petroleum recovery. Jordan Machnick is the lead energy, water, land analyst for the National Renewable Energy Laboratory. His primary work addresses the environmental impacts of energy technologies while seeking opportunities for energy and ecological synergies. Once they complete their presentation, we will hear remarks from Bob Lotz of the Arizona Public Service Company. Bob is the director of the Palo Verde Nuclear Generating Station Water Resources for the Arizona Public Service Company. In his role, he is responsible for ensuring a sustainable, cost-effective supply of water for the APS generating station. Fun fact, Bob has also been in this role for 36 years. I have my policy advisors with me, and anytime I mention anything before 1990, they always put their heads together and yell out, "We weren't born yet!" So Bob, I really appreciate you being on this call. He will be discussing what this study means to him as a utility person, past challenges, and future challenges. Vince and Jordan, the floor is yours.
Take it away, Jordan.
Great, thank you very much. And so I will be covering a little bit about how we've been able to characterize water use at different power plant facilities across the nation, some of the national in-scale work that we've done to help characterize how much water individual power technologies use, and what might be the impacts of some of those technology choices as we go forward. I'll then pass it off on to Vince Tidwell to talk more about some of the more nuances of the water use rates that we've evaluated for different power technologies. So going to the next slide, as Commissioner Rosales mentioned, energy and water are certainly interconnected. And this chart shows all of our energy flows on top in green, from primary energy all the way to energy use and energy disposal. And on the bottom, all the way, all of our water resources in blue, from source water to eventual use or discharge of that water. And you'll notice as you click one more, you'll see that the largest area of overlap is for thermoelectric cooling for electricity generation. About 40% of all the water that's used and withdrawn in the United States is used for power production. So this is an important feature that really means that water is an essential component for the reliable and successful operation of our power sector. If you click once more, you'll see that there's other connections too, with the water infrastructure also requiring a substantial amount of energy, but that's more on the order of 3 to 5%. Certainly nothing like the 40% of water that's used for power production. And if we go on to the next slide, you'll see that one of the reasons why this is so important is the fact that the dependency of the power sector on water means that there can be instances where you don't have enough water, or the water might be at too high of a temperature that our power plants cannot operate. And so this map shows over the last decade or so the dozens of different power plants that have had to curtail or shut down due to there not being enough water or due to temperature impacts of the water resources and how that prevented power plants from operating. So this is an important issue from an energy security standpoint and from a reliability standpoint, as well as from a cost standpoint. We want to make sure that our power plants are always operating when we want them to. And addressing the water issue is a key component of that. If we go on to the next slide, we'll see how really exactly that power plants do use water. And this diagram really highlights the two primary types of cooling systems that are in use today. One is a recirculating cooling in the upper left. Recirculating cooling is sometimes referred to as closed loop or cooling towers. And this operates by withdrawing water and using evaporation to help recondense steam back in the cycle. The other type of cooling system that we have is termed once-through cooling, and this withdraws in water in large quantities and through a heat exchanger is able to recondense that steam and then discharges that water back into the water body at a slightly higher temperature. This is a good opportunity. There's also other different types of cooling systems, such as dry cooling or pond-cooled systems, which can be a sort of a hybrid of these approaches. I'll be focusing mainly on these, but dry cooling systems are relevant and are important because they can accomplish the same cooling system needs, but sometimes at a cost and performance penalty. I'll take this opportunity, if you click once, to highlight that we will be looking at two different metrics when we talk about water usage in power plants. One of those is water withdrawals, and so water withdrawals is just removing water from a water body. So this is just the fact of water, taking water out, and you may or may not put it back. Water consumption is the amount of water that you remove from the system that you are actually not putting back. So this would either be evaporated or it might be incorporated into some other product, but it's essentially the water that's not available for downstream use. When we look at our cooling systems, the once-through cooling on the bottom withdraws in a larger quantity of water, but it puts almost all of that water back. The recirculating cooling, on the other hand, withdraws much less water than once-through cooling, but it ends up evaporating or consuming most of that. So if we go on to the next slide, I will show you some actual quantitative descriptions of some of the work that we've done to look at how much water different types of technologies use. And so this figure shows a lot there, but I just want us to look at some of the major trends. And so when we look at the middle column, that's for once-through cooling technologies. And you can see the water requirements there are anywhere from 10,000 gallons all the way up to 50,000 gallons per megawatt of electricity generated. This is a few orders of magnitude more than the amount of water that's withdrawn for recirculating cooling technologies in the left panel, where you see range from anywhere about 500 to right around 1,000 gallons per megawatt hour of electricity generated. Other technologies have values in between, but I think it's important just to highlight that we're looking at 20 to 100 times difference in the amount of water that's withdrawn for every unit of electricity that's generated for water withdrawal. Now, if we go on to the next slide, we'll look at water consumption. In water consumption, we see that the trends flip. And whereas before, once-through cooling withdrew a lot more water than recirculating cooling, in this case, once-through cooling has a lower consumption rate than recirculating cooling. Again, this is because the cooling towers operate primarily through evaporation, and almost all the water they withdraw, they end up consuming. And so what we see are higher levels of water consumption, anywhere from 1.5 to 2 to 3 times more water consumption for recirculating cooling than for once-through cooling technologies. We can also see differences, it's clear to see differences among different types of technologies here, where certain types of technologies have higher, or different types of fuel types have higher consumption rates than others. And if we click on to the next slide, we will see, if we just look at low carbon technologies, so we have both the range of the highest water consumption as well as the lowest water consumption. So on the higher end, we have concentrating solar power with wet cooling. We have nuclear technologies. We have coal with carbon capture and storage. Some of these issues are due to the heats that are able to be obtained and the resultant thermal efficiencies that you get, which lead to higher need for cooling water. And on the other end of the spectrum, on the right side, we see other low carbon technologies. PV, solar photovoltaics, PV, and wind require no water for operations, and some of the other dry cooling technologies are able to achieve generation with very minimal water use as well. But I think it's important to highlight that even if we talk about low carbon technologies, we really span the spectrum of high water use and low water use. And if you click once more, you will see an important point that natural gas combined cycle, one of the more dominant fuels and technology types that's been deployed lately, is really stuck in the middle between the high and the low end, but it has a much lower water use intensity than some of the other technology options out there. If you go to the next slide, one of the reasons why we talk about the power sector operations in general is because this is really where the lion's share of the water use happens. This figure shows just water consumption, but for the dominant cooling system configurations that are deployed, as well as how much water is used during the fuel cycle, as well as during the manufacturing of different parts. You'll notice that the green bars really dominate and that's all the power plant cooling. And so even though there is water required for uranium mining and processing, for coal mining and processing, and for natural gas extraction, even with hydraulic fracturing, it's still dwarfed by the amount of water that's used in during the cooling system and in the operations. And so this is oftentimes why we focus on this and why it's so important to focus on water use at the power plant itself. Going on to the next.
Jordan, I'm sorry, just a clarifying question. The CSP stands for what? Yep. That acronym?
Concentrating solar power. So that was on a previous slide. It's concentrating solar power. So it's.
Got you. Yeah. Okay, that's what we thought. Thank you.
Yep. So if we go on to the next slide, here we go. We're going to just do a brief overview of how these different technology types and their water use characteristics might affect future water use going forward, both on a national level and a regional level. And so here we looked at 4 different energy use scenarios. One was a business as usual, which is focused on, really has high natural gas. A second one has high renewable penetration along with some gas with carbon capture and storage. A third case has high nuclear as well as coal with carbon capture and storage. And the fourth has a lot of energy efficiency along with some renewables. And so going on to the next slide, and if you click once more, we can see what's going to happen with national level water withdrawals. And you'll see we're expecting, in the year 2050 to have drastically lower water withdrawals than we currently have today, partly due to regulations from the EPA that govern what types of cooling systems can be deployed and some of the environmental impacts of the cooling of once-through cooling systems. So essentially, we're seeing a transition away from once-through cooling systems into recirculating cooling systems or dry cooling systems even in some areas. But this is leading to a very significant reduction across all scenarios in water withdrawals. And so no longer will we be able to say that 40% of all water withdrawals in the United States are coming from the power sector. We'll see a much lower percentage. If you click on again, we'll go to and see national level water consumption estimates, and here we'll see, for scenario 1, the high natural gas business as usual, we're expecting relatively constant water consumption rates with a reduction going forward. And again, this is due to natural gas combined cycle, its relatively low water use compared to other existing technologies, and that really dominating and leading to a overall reduction. Scenarios 2 and 4, which have high renewable and energy efficiency penetration, do see reductions in overall water consumption from today's values. And scenario 3, which has coal with carbon capture and storage, as well as nuclear, we see sort of a dual trend of first a reduction and then an increase in national level consumption. But as we go to the next slide, I think the important point to make here is that water is really a local issue. And this is a complicated map that shows the major water basins of the United States, along with the regional impacts of those 4 different scenarios. And so if we go to we'll talk about the different regional impacts of each of these over the next few slides. So if you go to the next slide, this is for scenario 1, the business as usual with high natural gas penetration. Although overall we see relative reductions and relatively constant water use throughout on a national basis, we are seeing regional increases. And so those circled regions represent areas where we're actually expecting to see water consumption increases. And this includes some parts of the west, areas near Texas, and then some parts of the southeast and northeast. So again, just because national trends show reductions doesn't mean that you might see regional increases in water consumption in certain areas. And if you go to the next slide, we'll look at what happens in the high renewable case. And so this, even though we saw national level reductions in water consumption, there are still these areas in California and the Northeast where we might see potential increases in water consumption. And then lastly, on the next slide, you will see that we have additional impacts from the coal with carbon capture as well as nuclear scenario, that although by 2050 there could be an increase that are driven by those areas that are circled in the southeast, the southwest, the mid-Atlantic area, many other areas are experiencing water consumption reductions. And so I think the important thing, the takeaway that we want to make sure is clear is that water is really a local issue, and that national trends really, can mask the important dynamics that are happening on this regional level. The last slide that I'll talk about shows the impact of high energy efficiency case. And so this should be relatively straightforward, but if we're producing electricity because we're consuming electricity, we're going to have lower amounts of needs for both water withdrawal and water consumption. So that was a brief overview of some of the impacts that we're seeing and some of the results of the characterization of water use intensity of power generation technologies. Again, there's a lot of nuances in this that we can get to into the discussion. And I would say that there's opportunities certainly to reduce water usage, and that might be through either different types of cooling systems or, as I think Bob can talk about later, in the use of alternative water resources such as municipal wastewater or other things that could reduce some burdens on local freshwater resources. So with that, I would like to pass this off to Vince Tidwell to talk about a little bit more of the nuances and details that they're uncovering in examining why power technologies can withdraw and consume the amount of water that they do.
Thank you, Jordan. Next slide, please. So as Jordan mentioned, he helped explain why we see significantly different water use across different types of power generation, having to do with the fuel type, the cooling system that they're using, and a variety of other physical factors about the plant itself. In this study, we went kind of the next step and started to realize that the way the local utility operates that power plant also makes a difference in its water use characteristics. And this is fairly new because we're just now beginning to collect the kind of data that we need to be able to get at this more nuanced level. EIA and EPA together have been collecting some of this water use data, but more recently, particularly EIA has started collecting data on operations of the cooling system. And so this is, we started digging into this data. Next slide. And so this next slide shows us basically what we did is for every single cooling system in the United States, we plotted basically on the vertical axis the percentage of hours that the power system operated, and this is the net generation, versus the hours of the percentage of hours throughout the whole year that same system, the cooling system, operated. So looking at so where the cooling system operated the exact same number of hours that the its associated power system operated, it would plot along that dotted line. And so you can see a few along that line, but for the most part, they all the systems operate something below that one-to-one line. In other words, the cooling system in these cases are all operating more of the time than they're actually generating electricity. And in fact, if you look a little closer, you can see the different colored dots indicate different kinds of systems. So, and you can see a little bit of clustering, particularly nuclear. They tend to, because it's base load, tend to operate, up at the high level. So they're operating most of the time, both the cooling system and the power system. You can see the coal, natural conventional steam coal, largely kind of tends to operate at the higher capacity factors most of the time, but you can see a lot of exceptions, some other blue dots all over the place. You can see the red dots are really scattered across the whole spectrum. Those are the combined cycle plants. And then the petroleum in particular is down at the lower end of the scale in terms of the amount of time that they're usually operating. So point is here is the cooling systems tend to be operating more than the associated power system, and there is some relationship between this disparity and the kind of plant that it is. Next slide. And so we dug into this much deeper to try to understand what's going on. And so to help understand what we've learned is we drew this little schematic here on the right, and basically you can just think of this in terms of, a few days or a few weeks of operations and just to keep things simple, let's think of a generator and boiler connected to a single generator boiler system connected to a single cooling system. And so the green line is the operations of the generator, and that's its percent of full capacity operations. And then the blue line is the operations of the cooling system in terms of its full capacity. And so you can see that, generally the generator, depending on the kind of system it is, it's going to vary a bit, as it operates, depending on how the load in the system is operating or is varying. And so, but the important point is the cooling system, when it's on, it's on. When it's off, it's off. There's no following that load or that cycling of the generator. And so that light gray area is what we call this cycling gap. That is the time when the generator is operating at something less than full capacity while the cooling system is operating at full capacity. So you have a disparity in those two numbers. So the cycling gap is part of what we're seeing in terms of why we don't see the same amount of, or the cooling system isn't operated in lockstep with the power system. You also see that there's another thing going on here, and that's in these darker gray areas. And that's where at various times the generator is taken all the way to zero. It's idled, right? It could be that, the load is gone and you just need to shut it down, or it could be being shut down for maintenance or something. But there's always a period of time where that cooling system is still operating while that generator is taken down to idling. And so there's a good reason for that. Sometimes you have to keep that cooling system operating for a while to take away the latent heat in the system to protect the bearings and other parts of the generator and boiler system. But other times, you want to avoid scaling or fouling or other or issues when you dry out that system, or it's just too much of a trouble and you know you're going to have the system back up again, so you continue to operate that cooling system. So this is what we call the idling gap, that amount of time that cooling system's operating while your power system is being idled. So there are these two joint factors going on which give us that disparity between cooling system operations and the power system operations. Next slide. And so in this particular slide is we're looking at every single cooling system throughout the U.S. and the different colors are different kinds of systems: coal, natural gas, combined cycle, etc. And on the top is the idling gap. And here, so for every single cooling system, it's the number of cooling systems that operate. So that first big column there is 10% more than their associated power system. The next column is they operate on average 20% more, and etc. So you can see that most of the time, for most systems, they operate about 13%, when you take all this into consideration, about 13% more of the time than its associated power system. When they're idling, that cooling system is operating about 13% more time in a given year. And you can see it's pretty consistent across all the different fuel types. Same thing with the cycling gap. It's a little larger. We can see that about 30%, or the power systems operating about 30% on average less than full load when the cooling system is operating at full capacity. So about a 30% difference there. And so again, it's pretty uniform across all the different power systems, except early on they're in the 10%. So next slide. So in other words, there's a pretty big disparity between the amount of time that the cooling system's operating and the amount of time that the power system's operating. And for withdrawals, we can actually figure out that about 32% of all the water withdrawn is withdrawn at a time when we're not generating electricity. So either because we're idling or because we're operating at some load less than what our cooling system is. And in fact, you can see, so that the orange part of these columns is that amount of water that's being used when you're either idling or cycling. And so you can see that a good bit of that's because of the coal steam, because of the little black diamonds are the amount of electricity that's being generated. So you can see the coal, we're depending on most. There's a big gap there. The natural gas combined cycle, again, is the next largest generator, but has a pretty limited amount of additional water over that being used when power is being generated. As we saw in that earlier graph, nuclear is pretty low because it's operating all the time, so there's very little time opportunity for that cooling system to be operating when the boilers aren't. Natural gas steam is very high in terms of this cycling or idling gap, but you can see it generates a lot less electricity overall. So about 32% of all cooling system withdrawals occur when either the system is idling or through this cycling gap. So that gives you an idea of what the scale is. We would like to do it for the consumption. That's something we're looking at doing. It's a much more complicated calculation. So that's something we're still looking at to see how much of the actual consumption is related to this cycling and idling gap. Next slide, and the final slide here. So what we did try to do is go in more detail to see if we could relate and to understand why this is happening and whether this idling and cycling, this disparity between the cooling and power system operations could be related to a particular type of power plant, either, whether it's a coal or open loop or closed loop or different parts of the United States, or what could be contributing to this operation. And we did a large regression analysis with multiple different factors, and what we found is that, really there are exceptions to everything. Every plant operations were somewhat unique, and what it really looks like at the end of the day, what's driving all this is like what we would expect. It really has to do with the plant's place on the dispatch curve is controlling their operations. How often they're cycling and idling has to do with where they're at on that dispatch curve, and that's what's really driving this. And the important point here is that as more and more renewables are likely to be come online and penetrate the grid, you're going to see more and more of this cycling likely, and so these kinds of operational water use could become much more important as we go forward. So just as to sum up what we've seen here, you've seen Jordan talked a lot about the water use, the importance of water use in the power industry. It's the largest withdrawer of water, that amount of withdrawals and consumption depends on the kinds of plants, the fuel type, the cooling type, and there's big disparities there. I went on to talk a little bit about how it's also dependent on the operations of the plant in terms of how much cycling and as well as idling of those power systems. And then finally, Jordan also talked a lot about what difference does this make? Well, ultimately, as we go forward in time, those decisions we make about as the portfolio of generation changes, it will also affect our water use and our water consumption, and thus our exposure to drought, climate change, and other factors. And so with that, I will close and I guess turn it back over to Commissioner Rosales. Thank you.
Thank you, Vince, and thank you, Jordan. I thought that was fascinating. I just want everybody on the webinar to remember, if they have a question, please type it into the chat room, and we will get to it after Bob's presentation. But I found this, I found your presentations just fascinating, and there's a number of questions that I have. But Bob, I'm going to move it over to you. Give me some background.
All right, thank you, Commissioner. Here in Arizona, we have quite a history of water conservation out of here. So when the people, even before me, decided to build a nuclear power plant in the middle of the desert, it was a challenge to get a water supply for that plant, since we don't have any rivers or large bodies of water that could actually support that. So that's what drove the decision to use municipal effluent for cooling Palo Verde. So one of the things that I did for the past 10 years or so is look at how much water we're using in our state for generation of electricity. So I got with the other utilities in the state so we could put a holistic perspective together for us to see what our usage is for generating electricity in the state of Arizona. And I was pretty surprised that only about 2.5% of the total water used in the state of Arizona is for generating electricity, and we actually saw that decrease between 2010 and 2015, and that is in part with the implementation of utility scale solar that several of the utilities are starting to put in these days. About 70% of that water used in the state is from the Palo Verde Nuclear Generating Station use of municipal effluent. So some of the challenges we see today, although we've never had an overabundance of water in the state, there's an increased challenge in our water supply these days. Many of you may have seen or heard about the challenges with our water level in Lake Mead, and as a state, we're looking at decreasing amounts of water that each one of the lower basin states is being able to use, and that's increasing the competition for the water supply in the state of Arizona. So even municipal effluent is being challenged as a source of water that can be put back in the ground and used for other sources, other uses. So it's one of the things it's doing right now is impacting the cost of all water supplies, which kind of adds to our motivation. In my group, we've been looking at ways to reduce our use of water, whether it's alternative cooling technology, increased treatment, recovery of our waste streams that go to our evaporation ponds. We've been looking at all those things and looking at cost-effective ways to reduce our use of water. Hybrid cooling is being implemented on a new power plant that Arizona Public Service Company is building right now. It's a simple cycle turbine plant, and the estimated water use for that plant will be between 40 and 50 gallons per megawatt hour. So it's the first one of our plants that will be putting in a hybrid cooling technology, and we'll be looking at how that works for our plant. So the big goal of ours is to minimize our water use. Although, like I said at the beginning, in the state, our water usage isn't a huge part of the state's demand, but we also are looking at being as efficient as we can be. With that, I'll turn it back over to you, Commissioner, and we can ask questions.
Okay. Thank you, Bob. So here's where I come in as a commissioner and as a regulator, because in my experience here at the commission, I found to be there's two ways in which businesses tend to move. One is through regulation. Jordan mentioned that as well, with the regulations that are occurring in government with water. So usage is going to decrease to follow the law. Second one, as a former businessman, I have to tell you that I rather not go down that path, and I would like to, and I've seen that I've seen that efficiencies become available when they're cost efficient. So we're looking at other ways, other technologies in which a company will lower their costs by working more efficiently. What's concerning to me, and this is the reason why, as a regulator, I'm totally uncomfortable in making laws that are universal. It was Vince's slide that had the number of different plants, whether it was not even different types of energy plants, but different plants within the energy market itself, using having different degrees and different gallons of water usage. So when you have a blanket governmental law that pertains to everything, it doesn't sometimes, it doesn't do what it was supposed to do. I think we all agree on minimizing water usage is a good thing, But at what point, I'm going to throw this out to all of you, all three of you. At what point are we at a stage where how could we move forward? Because it seems to be so a vast array from one side to the other on the different power plants and in the uses of water. Where do we go from here? How do we become more efficient and try to make it so that it's more cost efficient for all?
Sure, I can. This is Vince. I can take a bit of a cut at that. And as you mentioned, one way of, I guess in this case, of managing the use of water in the power sector, one way of managing that would be through regulation. But what we're seeing today, to some extent, is that technology is having a significant impact on this water use. And with the, I guess you'd call it the gas revolution, the move to much more affordable gas and also much more affordable renewables, with some regulation there driving their penetration into the market as well, although their costs are becoming pretty competitive as well. What we're seeing is that overall, if as Jordan was showed in some of his slides, is that in many respects the overall water use, particularly, well, for sure withdrawals, but also to a large extent consumption is going down without strong regulation, at least aimed at reducing water use. So I think that's a very positive feature. So, one approach is by just being very attentive to the type of power generation that one is looking at and thinking about it in terms of the future water demand that has. So combined cycle, natural gas, PV, wind tend to use very, very little water, and those are many of what our capacity expansion, new added generation are in those categories. But there are other factors that can be employed as well, and that's looking at the source of the water that we will be using in the future. And while we didn't talk about it here, we'll probably talk about it in some of the other webinars, and is moving to alternative sources of water like brackish groundwater or wastewater, as Bob talked about with Palo Verde was a trend setter way back in the days, going with wastewater. Today it's pretty commonplace, particularly for power plants. And one of the nice things about those other sources of water is that they provide, in many cases, drought resilience, because they're not as exposed to variations in climate and drought. So the other,
well, I think, Vince, and I appreciate that, because and I know we'll get that to other webinars, but I'm fascinated by that technology. What the pushback that I've received as commissioner is that most water companies aren't built, to separate water in that respect. And so tell me how that would work, because again, we talked about efficiency of cost, and if it costs more to separate these types of water, like a brown water compared to drinking water, if it becomes cost, it's not cost effective, should we go down that route, or should we? I mean, is it something where we should regulate? Give me your thoughts.
Well, no, that's an excellent question, and you are right that it does tend to cost more per unit of water. And as we mentioned very early in the presentation, that energy use for water goes up, right? Because we have to treat it. So there's energy usually involved. Well, one way or the other, energy is being used to treat the water. So yes, it is more costly, although hopefully those costs are going down as new technologies are coming online is definitely the case, but it's still more expensive than, say, fresh water. But if you're also looking at having to pipe that fresh water in from long distances, now those costs are becoming very competitive. The other thing that you have to look at is that exposure to drought, and what is so if you're going with a traditional freshwater source, maybe a river or a lake, you have to factor in the cost that if drought were to hit and impact your operations, what would that cost be relative to wastewater, which, we keep flushing our toilets during drought, and, brackish groundwater's there during drought. So that's another very important cost, that disruption cost that you may be avoiding by going to an alternative source of water.
Okay, for all of you, let me ask, do you think when we come up with solutions, should we do this by states and by region rather than by having a regulation that's throughout the United States? Again, I'm going to the slide that you had, Vince, on on the different types of facilities and the water that it consumes. Is it more regional? I mean, when we talked about Arizona, Bob, 2% less. I mean, that was actually a surprising number, knowing of the challenges that you've had, with Lake Mead and some of the other places in Arizona, even talking about the Hoover Dam area. So do we need to do this by state basis? Your thoughts?
So this is Jordan. I can chime in here on this question, and I certainly do think that each state is quite unique in its water requirements and the type of generators and cooling systems that are deployed. For instance, west of Mississippi, there's only a handful of power plants that actually use once-through cooling technologies, especially on freshwater. Most of those types of technologies are concentrated on the eastern half of the United States. Most of the power plants in the western United States, like Bob's facility, have really thought through a lot of the drought issues and a lot of the water scarcity issues, and have sort of pre-planned for that. Whereas it's much more of an issue in the East Coast where facilities that assume they would have water too cheap to meter and that would always be there. They might run into some occasional droughts or temperature issues that might cause challenges. And so I certainly think that water is local. Keeping with the theme that water is local. I think developing solutions, whether they be technology related solutions or regulatory solutions or any other type of solution, is likely going to be more effective and more relevant on that local and on that probably statewide basis.
Yeah, and I'd like to chime in just a little on that too. And I agree with Jordan, the importance of that water issues are local, but there are many, though, policies at play which are having a big effect on the water footprint of the power sector, and not all of those policies are immediately aimed at regulating that water use, and they're at different scales or different levels. So one that Jordan pointed out earlier when he was talking is the 316B rule, EPA. So that's a national level ruling that states have to implement at one level or another, that is really changing the cooling systems that we're employing. And it has nothing, or the intention is not in changing water use, but is in the environmental impacts of the intakes of those systems. Another would be a state level policy, on the other hand, which has to do with your renewable portfolio standards, which again have an impact on your choices of power generation, which again feed back to your water use. So these are two examples of policies that are not really focused per se on on water use in the energy sector, but they have a profound effect on that. So anyway, I guess the important point is that when we think about policies, we really got to think about the whole system and think about these energy-water connections, and not just have our blinders on and just thinking about what they mean to the environment. Or emissions would be another place which would have a pronounced impact on water use. Okay, so and that would come at a state or national level. But finally, when we talk about water policy, when it comes to water use, states are the ones that have primary responsibility for making those decisions. And so that will probably remain in the hands of the states. However, environmental, your endangered species, your environmental flows is decided more at a national level, EPA and your fish and wildlife. And so again, very different policies have very different focuses on what they're trying to regulate, but ultimately have a big impact on the way we operate and make decisions about our cooling systems.
Okay, we're at the 8-minute mark here. We have a question from the audience, and for the three of you, let me want you to listen here as I repeat the question. Are there specific regions of the country that you expect to be particularly vulnerable due to projected changes in water availability and increased electricity demand? Anybody jump in?
Yeah, so this is Jordan again. This is actually the subject of a future webinar in December, where we can get into a lot more detail on that front. But this
good. It's a good time to plug that webinar in December.
Yeah.
When in December is that going to be?
Was it December 3rd?
I believe, isn't it, Kerry?
Yeah. Yeah. But I think as a quick summary, as I mentioned, a lot of the although you might think, the arid West, is going to get hotter and drier, and they might have more issues. As we mentioned, facilities like Bob's have already, done a lot of thoughtful thinking and planning, and so we're actually, given the variety of different scenarios of water availability, water temperature, electricity demand, we're actually seeing the higher likelihood of issues in the Southeast and the Northeast and the Midwest, where we might see water-related impacts and water-related curtailments or shutdowns for the existing power fleet.
Okay. All right, it's just about time to wrap up, folks. I want to give you one last opportunity to tell me what you would like to see occur, and I like Bob in terms of, as regulators, I gotta admit, when we're thinking of our resource planning, integrated resource planning, that hasn't come up when we talked about electricity, and that's the first thing that I'm taking. That's my first takeaway from this webinar is when we move forward, thinking about the water usage of how we go to when we do our planning. It's I found that to be very fascinating and well worth the time. But for everybody else, what would you like to see from us as regulators as we move forward?
Well, I'll just go back to my previous comment, and that I think it's very important as you consider policy related to the energy sector to also be thinking broadly and or looking for feedback from those who are engaged with the water sector to understand what those trade-offs are across the board, not just, what are the implications for the energy sector, but more broadly, how it affects the water, the environment, et cetera, and how that then feeds back again to the energy sector.
Mm-hmm.
Commissioner, this is Bob. Okay. One of the things that I think is very useful is for the utility sector to try to educate other sectors on what it is that we think we can and can't do, and how that can impact our cost of operation. I've said before that we can go to dry cooling, but at what cost, for what benefit? And that's where I think we all just should get on the same page with what is it that we're trying to achieve and what is the benefit that all of our customers or constituents get out of that. And so just that interaction and that dialogue, I think, is pretty useful.
Jordan?
And, I wholeheartedly agree with what Bob and Vince both said. I think those are great ideas. The only other thing I would want to add to that is, at this point in time, the electricity sector is rapidly changing, with the inclusion of not only that, the natural gas combined cycle boom, but then also, the increase of PV and wind, adding some more variability to the system. I think, at this point in time, there's a lot of changes that are happening, and that the focus of regulatory actions or of other incentives or other activities should really be focusing on what are the impacts 5 years or 10 years down from now. How can we have a flexible structure that can adapt to the changes that we're seeing that are ongoing right now on the system? So I would really push for looking 5, 10 years and even further beyond that for potential new areas of vulnerability or resilience concerns and how we can address that.
Great. Jordan, Vince, and Bob, I on behalf of NARUC, I really want to thank you for your time and appreciate you being part of our first seminar. Carrie, we're going to conclude the seminar for today. Again, I want to thank everybody for participating and for the number of those that have, we see there was a number, looking at the chat room numbers, there was a number of folks participating throughout the country. Thank you for being on. I hope it was worthwhile for you. Certainly was worthwhile for me as a commissioner. Carrie, thank you again for the opportunity to moderate, and we will now adjourn the meeting. Thank you all for your time. Have a great day.